Hello, welcome everyone to the next session is Human in the Loop session. As we know, we're talking about the whole in the conference, human in the Loop is really bring the human back to the self-adaptive systems, so that the human system can cooperate to achieve some shared goal. And in the meantime, the human and system behavior mutually influence each other. So we have 4 exciting papers in this session. To keep everybody in the loop, my name is Xi Hong from Florida Atlantic University. So the first paper will be presented by Sherry in collaboration with Javier, David, and Bradley from CMU and York University. The title is Hey, Preparing Humans to Do the Task in Self-Adaptive Systems. The format is each person gonna have 5 minutes or so, present their work, and we're gonna have question and answers at the end. Hopefully we have a good discussion in our session. Okay, here we go, Sharon.
Hi, thank you. Can you hear me?
Yes.
Okay, thank you for your introduction. Yeah, I'm Sherry. I'm Nian Yuli, a PhD student from Peking University. I'm pretty glad to have this chance to introduce our group's recent research, Hey, Preparing Humans to Do Tasks for Self-Adaptive Systems, which was collaborated with my colleagues from Carnegie Mellon University, Peking University, and the University of York. Okay, let's start from the 3 stages of evolution of software systems. At very first beginning, software systems would require frequent human intervention because they were not designed to deal with uncertainty. Around 2 decades ago, we came to the self-adaptive era, and the ultimate goal of self-adaptive system is to eliminate the need for human intervention while adapting to the changing circumstances. However, the human operator is not useless. They can actually provide some expertise, which is not easily automated. As a result, we came to the 3rd era, the co-adaptive era. And in this new era, humans are involved to achieve system objectives with their diversity of skills, availabilities, and abilities. In terms of human involvement, there are 3 main design principles. The first one is to complement functionality, meaning that humans are collaborated with the system to execute certain tasks. The second one is to achieve understandability. Human must understand what the system's data are and how the system operates. Otherwise, human may mistrust the system, leading to an inefficient collaboration. The third one is to manage human preparation. Human can be distracted or focused on another task at the moment when the system requires his participation. The system must perform effective actions in order to get human mentally involved to improve effectiveness. So to implement these 3 principles, we could consider human assistance of a certain task, system explanation, preparatory notification to an operator, each one as an explicit tactic to optimize system goals. Despite the fact that these actions or tactics can positively yield positive effect, it may also bring with cost. For example, preparatory notification can yield positive effects due to attention management and context awareness of the forthcoming task. It may also bother humans' current activities. So it is non-trivial but important to reason about when and in what form to use preparatory notification. Too late or too little urgency of the notification, and the human may not be effectively prepared. Too early or too much urgency, and the human operator's level of attention may progressively degrade, thus wasting his preparation time. So in this work, we will apply a formal framework by following our previous research for designing human-involved self-adaptive systems, where preparatory notification can be used as a tactic to proactively aid the human operator. We model human and system as a stochastic multiplayer game and allow a probabilistic model checker to determine the optimal use of preparatory notification. And the key to this framework is the explicit use of human attention to refine human attributes model. In this work, we only focused on the 3rd principle, manage human preparation. To further understand how we implement the first 2 principles, please refer to our previous work. Okay, here is a high-level view of the time axis. our preparatory framework will proactively notify the operator before assigning the task. The lead time here denotes the interval between the instant in which the preparatory notification is received by the operator and the start of task execution. The optimal lead time will be the minimal time required for an operator to make a full preparation. Notification here can be used to simultaneously manage human attention, shifting his attention from the current activity to the forthcoming task, and allow operators to comprehend the task context. Attention management is about how much mental concentration an operator has on a task, whereas context awareness is about how much understanding the operator has of that task for efficient task performing. In terms of attentional shift, its speed is greatly influenced by the task type and task urgency. We combine these two factors into task priority, where high priority denotes an important task with high urgency. Okay. In terms of context awareness, time to achieve context awareness is proportional to the complexity of a task context and inversely proportional to the training level. Operators' training level contributes to the ability of assimilating the context information faster. Besides, attention could also affect context awareness. It is intuitive that when operator is not paying much attention to a task, he cannot efficiently comprehend the context, even with a high training level. So to this end, we'll take three factors into account: task priority, context complexity, and training level to synthesize adaptation strategy with preparatory notification. The optimal lead time of preparatory notification will be figured out by model tracking the stochastic multiplayer game, so that operator will be informed with the right time and the right form of the notification to make proper preparations. Here are the analysis results for a delivery scenario where an operator and a mobile robot will collaborate to complete the delivery task as soon as possible. Interested reader can refer to our paper for more information. Okay, so in this work, we presented a general framework based on probabilistic model tracking to determine when and in what forms a notification should be used as a tactic. Actually, this paper is just one step of a series of human-involved adaptive systems. Although one limitation of our evaluation is that we did not directly correlate our analytical results with the actual systems through an empirical study. Our results are supported by and consistent with the existing empirical user studies from psychology field. Also, we only consider one operator for a delivery planning task as our running example. Scenarios with multiple tasks and multiple operators can also be considered in future work with additional task allocation and task allocation module. Yeah, that's the end. Thank you.
Thank you very much, Sherry. It's a very, very nice, interesting paper. We do have some questions from the chat. Let's Anna asked this question that, can you please discuss how do you see the relationship between the self-adaptive and the co-adaptive era? The way it was presented gives an impression that you consider the co-adaptive era as a succeeding era after the self-adaptive era. But I would argue that it is the opposite, that the co-adaptation era is the prerequisite for the self-adaptive era.
Actually, based on the papers I read from the self-adaptive community, I believe that the co-adaptive era just started around like 4 or 5 years ago. So I wouldn't think this co-adaptive era is pretty mature. Actually, I think we still have a lot of work to do. Yeah.
Okay, great. Thank you. So we have a question from Radu.
Xihong,
Yes.
sorry to interrupt. Can you make all the presentations and ask the questions at hand from
Great.
5 minutes? Okay, fine. So every presentation, 5 minutes. In the end, you open the discussion. So everyone, sorry about this. All right.
Okay, yes. Okay, so in terms of time, we better move on to our next presentation, and we have a discussion at the very end. So the next paper is a conceptual reference model for human as a service provider in several physical systems. We're going to present it by Hargova from University of Birmingham.
Yeah, thank you very much. I hope everyone could see my screen now. Yeah. Okay, so hello everyone, I'm Hargyo. I'm a PhD student from University of Birmingham. So I'm pleased for this opportunity to present our work in conceptual reference model for human as a service provider in cyber physical system. So human-machine collaboration provides flexibility in human-in-the-loop CPS. Machine with computing ability is superior on speed, accuracy, and so on, but human with his cognitive ability to help the machine dealing with unanticipated circumstances. But the role of human in the loop is generally operator, service consumer. Human use the service provided by the machine, not the other way around. So machines are not enabled to request service from humans based on the competencies possessed by humans or based on other human parameters and attributes. In fact, however, in many complex systems, we see that machines and people work together to achieve system goals. So in this sense, we would advocate that human could be service providers instead of service consumers only. So our ultimate vision is basically to transit the problem of service composition into collaborative human-machine service composition where bidirectional, info-symbiotic cooperation, learning between the machine and human can be envisioned. So to enable human-machine service provisioning, we need to have a knowledge model that both human and machine could understand. And I think ontology is one good alternative. However, existing models are not adequate enough to enable human-machine service provisioning, where human characteristics are not explicitly modeled, and also humans are mostly considered as physical entities, similar with robot sensors and other actuators. So we try to classify types of service that human can offer to machines. The first is sensor service through human sense or social sensor. Second, processing service using human cognitive ability. The third one is actuating service that may involve physical activities. And the fourth one is adaptation service, which is a composite of the three services above, where human act as an adaptation promoter for other component. Then this role includes, but not limited to, the control feedback, provision of knowledge, learning, and also evaluation of the self-adaptation. So as solution for this problem, we propose a service-oriented architecture model for human-in-the-loop CPS. We express it as an ontology. We use ONET, Occupational Information Network, as primary reference to build our human service capability model that come from the notion that every task that we or human carry out in our work routine is basically a service. So we have job, basically we provide services to other parties within our company, organization, system, wherever we are currently in. So in the ONET framework, every single job requires different selection of knowledge, skills, and abilities to perform various tasks and activities. And these human credentials will determine the range of services and also the quality of services that human can provide. So here we could see that human and machine are physical things with distinguished capability to perform tasks in many different contexts. And during the completion of their tasks, they could help each other as service providers or receive help from other service consumers. So to allow adaptive human-machine service provisioning, our model taking into account the machine and human capabilities. So here, as you can see, that we define human capability as human characteristic, human qualification, human potential, and yeah, and under human characteristic, basically psychophysiological factors that distinguish human from one to another, and qualification are attributes that describe person's fitness to perform the task. Then potential is a latent human capacity to improve for growth and development. And under human characteristic, we have preferences such as time, location, price, and also abilities that express innate human attributes, with physical attributes, cognitive attributes, and so on. And also we have performance factors, which are internal and external variable aspect of human behavior, such as ergonomics, work value, work style, and so on. And also we have knowledge, skill, experience. Those are similar to ones that mentioned in ONET framework. So if we use we use our model to work together with MapK loop. I can give you an example that we use a hierarchical control pattern where we have 2 layers. The first layer is service broker that in charge of service discovery, composition, provision strategy, according to the criteria given to the service consumer at the second layer. And the second layer is the self-adaptive system with their own MapK loops. Their system interact directly. All of them share knowledge, and then depends on the service flow direction. One could be service provider, and the other party can be service consumer. So we enable human machine or machine collaboration in this sense. So as you can see in our paper, we provide quantitative and qualitative evaluations that we do to assure that our model or ontology adheres to certain desirable criteria such as clarity, consistency, accuracy, completeness, and also adaptability. I think that's all for now. Thank you very much.
Okay, thank you very much. So let's move on to our third paper, is maintaining driver attentiveness in shared control autonomous driving, going to be presented by Radu from University of York.
Hello, everyone. Can you see my screen? Hopefully you can hear me as well.
Yes.
Very good. Thank you. So yes, I'm Radu Calinescu. This is a joint work in progress with my PhD student, Naif Al-Asmari, and with my postdoctoral researcher, Mario Glacier. And our research focuses on level 3 driving automation, in which cars are provided with automated driving systems that can perform the entire driving task, but only within a limited operational design domain. For instance, on specific types of roads and in certain weather conditions. And this is only possible if a couple of requirements are satisfied. First, the driver needs to quickly respond to requests from the automated driving system to resume manual control of the car. And second, the system itself needs to detect whether the driver is attentive, to provide warnings otherwise, to issue a demand for the transfer of control back to the driver if the warning continues for a certain period of time. And finally, to start a minimum risk maneuver if the driver remains unresponsive. That's an euphemism for stopping the car safely. So we propose a human-in-the-loop self-adaptive system that aims to achieve these requirements. And in our solution, the driver and the car are monitored through a number of sensors. The sensor data is then analyzed by an analysis module that is based on a deep neural network to identify the level of attentiveness of the driver. In this diagram, green stands for the driver being attentive, red is inattentive, and there could be a number of amber levels in the middle, meaning semi-attentive. Changes in the driver attention level.
Radu, sorry, but we only see one slide, the first slide. Can you move the slides forward?
That's
just
not, useful. I have moved the slides forward. Let me see if
we're seeing your PDF screen here. Yeah.
Now we can see the new slide.
Right.
Okay.
Well, I'll keep it like this rather than maximizing it to the entire window. Right, so here again is the solution which shows how the driver and the car are monitored, and the sense data from the driver biometrics and the car status is used in analysis to establish whether the driver is attentive, that's green, inattentive, red, or semi-attentive, that is amber. Changes in the driver attention level trigger the discrete event controller, which can itself switch on and off a number of alerts trying to raise the level of attentiveness of the driver. Those could be optical, acoustic, haptic, and so on. Controller also has the opportunity to vary the speed of the car. And the overall goal of the system is to achieve a optimal trade-off between the risk level due to the driver being inattentive, nuisance caused to the driver by switching on alerts, and progress with the journey, which will be impacted if the speed is reduced. Much of the work on the analysis module that is based on a deep neural network has been completed by other teams within the project, and there are research papers that discuss this work. So this paper focuses on the synthesis of the discrete event controller and the overall solution. And this synthesis is carried out in 3 steps. In the first step, we model the design space of the controller as a parametric continuous time Markov chain, where the parameters correspond to different controller actions that can be taken at various stages of the process. We then, in a second step, define properties such as risk, driver, nuisance, and journey progress that are associated with different model states. And finally, we use this design space to synthesize controllers that are Pareto optimal. So detailed technical descriptions are provided in the paper, but this diagram gives you a flavor of how the models look like. So these are state transition models. Initially, the driver will be attentive, controller is inactive, all the alerts and the speed reduction are switched off. But out of that state, the driver might transition to the state where they are inattentive. That will activate the controller, which then has the option to activate, to switch on a number of alerts to reduce the speed. So there are 8 options here. As a result of those actions by the controller, driver might resume being attentive, in which case the controller will immediately switch off the alerts. There is no point in keeping shouting at the driver if they are fully awake. But otherwise, the timer will reactivate the controller every so often to give it the opportunity to switch on additional alerts should that be needed. So I mentioned that there is a second step of the approach, and in this step we define the levels of risk, driver, nuisance, and journey progress associated with different states of the system. As an example, the nuisance will be non-existent if no alerts are used, might be medium if the optical alert is switched on, and so on and so forth. We take then this parametric continuous time Markov model, and we use a stochastic model synthesis tool called EvoChecker to identify Pareto optimal combinations of parameters of actions of the controller, with the aim of achieving these conflicting requirements to minimize the risk, driver, nuisance, and to maximize the progress with the journey. And this plot shows the solutions that were produced for a 4-hour journey through this synthesis process. Each point on the Pareto front corresponds to 1 instance of the controller. So you have the opportunity to then decide whether you are going to minimize the risk, maximize progress with the journey at the expense of having the maximum nuisance to the driver, or maybe you want to reduce that nuisance towards the left-hand side of this 3D plot, and that will increase the risk or reduce the progress with the journey, or both. So what we achieved here was to develop a human-in-the-loop self-adaptive solution for maintaining driver attentiveness in level 3 autonomous driving, which involves monitoring the driver biometric state of the car, carrying out analysis through the use of a deep neural network, planning driver alerts, speed changes to the car, and finally executing this plan through using a variety of actuators. We want to move next to a stage where we can actually use results from the verification of the deep neural network, so we can integrate machine learned components and traditional software components within the MAPE-loop in a better way, and we would use those to calibrate the predictions of the deep neural network. Finally, we want to improve the accuracy of the controller by personalizing it for individuals, adapting it as it is deployed, and ensuring that it is sufficiently robust to inaccurate predictions by the neural network. So this is the work in a nutshell, and I'll be happy to answer questions at the end.
Thank you very much, Radu. Let's move on to the next presentation, and then after that we have our discussion. So next presentation is a gamified and semi-adaptive system application for common good. Research challenges ahead. So this is in collaboration with the 3 universities.
Thanks a lot. So do you hear me?
Yes.
You see also my slides, okay?
Yes.
Yeah. Okay, thanks a lot. So my name is Antonio Bucchiarone. I'm a researcher from Fondazione Bruno Kessler in Trento, in Italy. So this is a vision paper together with my colleagues in FBK and Antonio Cicchetti, Sweden, and Nelly Bencomo from UK. So in this paper, our goal, so our main motivation is to put in some way communities and the citizens together to find a common good for the future, no, to be more sustainable in general. Okay, so and to do this, we need to engage people. We need to engage people to behave in a certain way, to change some behavior that's in general can help to improve the status of our life. So we want to change the way they behave in such a way to combine their positive and negative behaviors, and in some way to give them virtual and real incentives to change what is negative now that could be positive in the future. So in some way, we have also the aspect of micro communities. So people are not together, are not alone. So they should live together, and they need to contribute to create a community of active users. So we have to target specific users or specific type of users, and we need to deploy specific actions for these communities. So and create synergies with other local initiatives. So our main goal is to create a system that is based on a multi-challenges management. So micro communities participate to multiple campaigns that are devoted to find the common societal goals. So to do this, so our vision is to implement advanced technologies to exploit this network of people and have an impact in the communities. So we want that they collaborate to reach the common good by sharing the strength of the people, but also improving their weaknesses. So how we do this? We have an approach that is composed by 3 different concepts. So first of all, we have a social capital. So each people, each group provide a set of individual capabilities and can contribute as agents to solve specific societal challenges. We would like to improve the inclusion of people. We want to reduce the environmental impact and want to have healthy habits from them. The second aspect is citizen engagement. So we want to involve people in game-like scenarios where their tasks will be accomplished in a certain way and will be rewarded with the virtual or physical prizes. So for this, we want to have a personalized and adaptive gamification. So to engage them through games and try to adapt their individual behavior in order to reach a common goal. The last aspect is we want to have a multi-challenge motivational systems. So here we want to introduce a new paradigm where micro communities will participate to multiple campaigns that are devoted to common societal goals. Communities are formed on an appropriate combination of social capital that contribute by each individual. So the system that we have in our mind is composed by 3 main pillars. So we have the aspect of multi-agent systems and AI techniques to engage them and to put them together in the same system. We have gamification techniques to engage people to change their behavior and to afford specific actions. And we have self-adaptation that is very important because during the life of this kind of application, we would like to adapt the system when we discover that something is going wrong and we have no reaching the effect that we want at the same time. So our vision is composed by two main loops, one that is for the city and the second is for the citizenship. So the first is the classical map loop where we have the monitoring phase where we want to understand the status of the city and to help the administration and companies to understand the city and how it evolves. So the second is the analysis. We want to digest this data and provide alerts when they are needed. So to understand the real situation and what could be the societal challenge that we want to achieve. So in the plan phase, we want to provide a set of plans for the group of citizens, for these micro communities. We want to partition the group in a certain way. We want to distribute the consensus, and we want to deliberate plans to these communities. The last phase is we want to engage and execute these plans, engaging people with the customized challenges in order to incentivize the behavioral change of these people. The second loop is inside to do the main loop and is for the citizenship. So we have 4 phases. So the engage, the act, the learn, and adapt. So the engage is for engagement of the user and for the customization of the specific challenges in the micro communities. So in the act, through gamification, we incentivize people in order to boost virtuous behaviors. And here we can instantiate, for example, collaborative or competitive challenges in the gamification engine. The third action is to learn. So we want to understand what is the impact of the actions in the different micro communities. We want to have the picture, the real-time image of the city to understand the health status of the city. And the last is to adapt. So manage the critical issues of a city to adapt both the engagement strategies and define, for example, new challenges for the micro communities. So our vision is composed in this picture. So we have 3 different loops, for example, that are targeted to 3 different sustainable societal challenges like mobility or carbon neutrality or health and well-being. We want to put together in 3 different loops, and they share the knowledge that represent the status of the city. And inside to each loop, we have the citizenship loop that is based for the engagement and participation of citizens. So finally, what are the open research challenges? For example, we have to manage the inclusiveness and support the engagement. So we have citizens with different profiles and different backgrounds, and we have to target specific techniques for this. We need to manage the adaptiveness of the system and the continuous engagement. So this is a system that is every time adaptive. We want to evaluate the positive behavior of the change. So and also the negative in order to adapt the system if we need. And finally, that is very important, we want to include also the privacy and the ethical issues when the citizens perform these collective behaviors using the shared knowledge. So this is about our vision. So if you have questions, please contact me by mail or later in the discussion. Thanks a lot.
Thank you, Antonio. It's a nice presentation. So now I will open the floor for questions. First, I will pick up some questions from the chat box, and then if we have more time, we can have more questions come up. We must finish our session by 11:10. So the next question to Sherry is from Rado. Do you expect your solution to require calibration for each human operator using it, and how would this calibration be carried out? You're muted.
Okay, thank you for this question. Actually, I think I could answer also to Colin's question, because you have the similar questions about how to deal with situations for different person, right? Of course, we have already taken that into our consideration. If you remember my presentation, we take 3 factors. The task priority, which will determine the attentional the speed of attentional shift. For example, if you have a very high priority task, of course, you will shift your attention in 1 second, of course. And the second one, the second factor is the context, the complexity, the context complexity, which will affect your time to comprehend your task right? And the third one is your training level. So for different person, the training level would be different. And for Colin's question, so how would I consider the capability for a different person? In my work, I consider the capability is determined by the training level and attention. So so this is what I did in this work. Yes, of course, I consider these three different factors. Yeah.
Thank you.
Yeah, so thank you very much. The next question is from Danny. So
Yes, shall I say quickly? So thank you for your talk, Niang Yu. I see that your work is focusing on one direction, but the interaction with the system is often bidirectional, or the interaction can also be in the other direction. Think about Jeff's keynote in the first day. So I was wondering, what is your thought on that? Would a similar problem emerge in the other direction, or is this probably another type of problem? I just want to hear your opinion.
So your question is whether the system should have certain attention when the human operator requires the system's task, right?
Exactly.
Actually, I haven't think about that question before, but in my opinion, I think attention is very human-like thing. I wouldn't think the system would have attention or not.
No, but if a human, your work looks at the direction as a machine, I want attention of the human. But if a human said, I want attention of you as a machine might also be busy, yeah? Might be busy with all kinds of stuff. And then now it requires attention from you. Okay. So I was just wondering, okay, it's a more speculative question, I know, but
I wouldn't think we would use the term of attention. Probably we can say, okay, whether the machine has some time for me or not.
Yeah.
But if you want to say the machine has attention or mentally free, it's kind of awkward for me.
Yeah. But still, if we go in this direction of man-machine interaction, something, it is just a matter of you can consider as a thought for inspiration, let's say. Thank you.
Yeah. Thank you for your inspiration. Yeah, we can consider that direction in future.
Danny, I think for the system to the attentions of a system to human might be through the form of explanation. So of course the system doesn't have the emotions, all the emotions your eye tracking. We talk about in the self-driving car by Radu over there. But how the system get feedback to human, I think the system get feedback to human through a proper explanation. So if humans say, I need some attention on some certain point, I don't understand, I'm confused, and the system could tailor their explanation towards human to see in which stage, in which form you need my attention more. And I think explanation would be one of the form to communicate from system back to human. It's just the way I'm taking it.
But if I just may, a few seconds, think about this talk of Jeff Keppert in the beginning, where he was saying like the interaction between a man and a machine. He was arguing it should be multimodal. We are tracking the eyes of people in our interaction, and a machine should also learn to have this kind of multimodal interaction. So it fits a bit in that space what I was trying to post here. But again, it's more speculative. It doesn't say anything about your work, Niang, so don't misunderstand me, but just a thought. Because you focus on one direction, I was just curious, what about the other direction? That's it.
Absolutely. That's interesting. Yeah, this co-adaptation part. So we have one more question for Sherry, but let's move on to a question to Radu, and then we can come back to one more question to Sherry. So this is nice work.
Shihong, maybe we can ask if the author of the question would like to make the question themselves.
I'm sorry, what?
So instead of reading the question, we should ask if the people who wrote the question would like to make the question.
Yeah, that's a good one. Yeah. So Gina, could you answer your question to Radu, please?
So it's a question from Radu, right? Radu, do you like the, would you make the question, please?
No, Radu is the one being asked the question.
Okay, who did the question?
Yes, it is. The question is from Tinana.
Oh, right. Okay, okay, that's me. Right. Okay, good. So Rado, I was just curious here. Actually, I feel like, I'm not sure if that's right, but I feel like there's a kind of a, how can I say, a complementary between the work of Nianli and your work, but I feel like your work, it goes more into more technical details, and is something that I really like in your work, and somehow I missed in the Nianli work. So this is really cool. But my question here is mostly about the criticality level of the actions that you take. Has it been considered in the SCADA? It's more like clarification, right? It's just my curiosity. I was wondering if something like, as you guys use the, not sure if that makes sense, but at least the things that you used in the awareness requirements in interest work, if there is anything that it could fit in here. So kind of depending on the situation, then the alert could be more emphatic, or even like without waiting for the human to answer for like, yes, the alert is really going on, and we should just pull over the car, and for the safety of others, or the context, for example, like if it's snowing situation, something like that.
Yes, I believe you are asking whether one should use different levels of sound, different sounds for the acoustic alert, for instance, in different circumstances. That is allowed by the framework we put in place by this platform. We haven't necessarily looked into it because we regard that as sort of orthogonal to the project, but we will choose from work done by other research communities, suite repertoire of such alerts.
Yeah, I was wondering this because I feel like, as you mentioned, like it's orthogonal, and that there's a kind of many cross-cutting concerns here, not only from the modeling, but also from the environment. And I understand like the domain in the from the drive, the autonomous driving, industry. So there are lots of concerns here, and many details that should consider here. So I guess this kind of information is hard to have like an expressive or comprehensive way to represent all this information into, let's say, the same model that you guys have built. But okay, thank you.
This is indeed very complex. So I think the best thing to do is possibly what we did, namely to build on top of a international regulation. So we took a UN regulation that was published last July, I believe, and we use the requirements from there. Otherwise, we would just make them up ourselves, and that wouldn't be wise.
Thank you, Rado.
Okay, thank you. So we have a next question to Antonio, and Colin has 2 questions. Would you please phrase your questions?
Yeah, thanks, Antonio. I guess it's a higher level question, which is, shouldn't we be a little bit afraid if we're developing systems to change people's behaviors? Social engineering doesn't have a very good reputation.
Yes, this is a good comment. So we want to change their behavior in what they already do and improve their goodness. So I can give you an example. We have a gamified system here running in Trento, another city in Italy, for smart mobility. Okay, so every time that you reach, for example, your office, okay, and you can use different transportation means. What we want to improve is the usage of bikes in a certain period of the year, for example. No, so this means that people that would like to use the bike can use the bike also to go to the job. Okay. So, and with these challenges, in some way, we improve their goodness because they love to use the bike, but usually they don't do for reaching to reach the job location. So, and we engage them to do more in this sense. Okay, so we don't want to extremely change the life of people, but in some way engage them more in what they are able to do. Okay. And in this case, we discovered that if they have the right incentives that usually are not every time monies, but are a different kind of incentives, they can use the bike more in certain period of the year. But in different application domains, we can have a lot of examples.
Yeah, I don't disagree. But it is a challenging thing to do. You might want to look up the Cobra effect from economics, which shows the good is not always leading to good.
Yeah, I agree. But we also discovered also negative aspects, so how they try to force the system and how they want to, for example, there was one player that simulate the mobility application with the simulator without to move their foot from the house. And so we see also these kind of aspects, and this is part of the life.
Yeah. Okay. Thank you.
You're welcome.
Okay, great. So next question is from Danny to Antonio.
Yeah, Antonio, you probably already read it in the chat. I mean, I really like this kind of visionary ideas, but I was a bit searching for, I mean, from a technical point, let's say. Of course, the whole talk is not really so technical. It's more. But I was wondering if you talk about, you used a few times the word system, but then I was looking what type of system are you talking about? And then you talked about adaptation. Is a system a city, and is he the adaptation, the controller, the human, or are there really technical systems involved here?
No, here this is a very complex system because we have the IoT part that monitor the city, so the Internet of Things. And we have the human part through mobile apps that are used by the humans. And we have the controller that in some way monitor the situation from each single behavior, each single player. For example, in the previous example, if you have a mobile app for that you track your journeys every day from your home to the job, okay, you know the story of the player, no? You know the story of the employee. And you can, in some way, understand what is the common behavior of these people and try to suggest some challenge to this player. No, so you monitor that every day the user go by car, but when there is sunny day, he prefer to go by bike. Okay, and we can also suggest, please use more the bike. Also, when there is raining not so much, you can use the bike also. Okay. And through the app, we can also provide this challenge to the player. If the player accepts, can in some way accumulate points in the game, and in some way we can introduce also adaptation of the behavior of the system, no, through new challenges. We have also introduced challenges, for example, to engage people together. No, I can invite people to play with me and to reach a certain score. Through our mobility behavior. So if we use the bike together every day, we accumulate points together. So in some way, you also can create a community, of positive behaviors. And so I don't know if I clarified the question.
It helps. I see it. And within the level of abstraction of your vision, I can understand to give it a place. Thank you.
Yeah, welcome. Thanks a lot.
So the next question is Iles to Antonio.
Yes, hi Antonio. A lot of questions to you. No, I was thinking along the lines of Danny, but now I have another question. Do you think that the trust is an important issue in this kind of socio-technical systems? Because of course you can have nudging mechanisms, right? And you can have gamification being part of the story, but how do you make sure that people trust that if I take a longer route or if I go by bike, unless there is some kind of network effect that others do the same, there's no real effect in the system in many cases. So how do you build? Have you had any thoughts on the vision around the trust that needs to be built? Is it key?
Yes, of course, it is a key in the sense that to explain to the player that every day they are tracked, and this tracking system is a valid system because you need to reward their behavior with the precise reward, that is calculated automatically. Sometimes they say, so I don't trust your validation system, and this is a research challenge. So we have a lot of algorithms running behind. So that's track the player and try to understand using AI which kind of transportation means he or she is using in a specific moment, and that sometimes we can have also not valid tracking values because you are using the bike or the car, for example, and you are in the traffic and the speed is like the bike, and sometimes you have a wrong result from these components. So there are a lot of research challenges in this, especially to use AI, but also the context that can help you to understand if this is really the bike, So you can, using map information to understand the type of roads, if this is the road.
This maybe goes beyond the AI, I believe, or rather orthogonal to it, because I think some people, for example, that was mentioned before, some social scientists, they really kind of drill in the ways people are convinced, and the patterns of convincing people without them feeling that they are overwhelmed by the system or that the system knows more than they wanted to know, etc. So it's very interesting, all what you say. I just believe that there's an element of this social engineering which is very, very difficult, as Colin said, and very challenging. It goes totally beyond whether
I agree with you. And this is why when we develop this application, so we don't consider only the technical part, we consider also the social part. So we engage the citizen directly to design the requirements of these applications through, citizen science techniques and involvement of group of people that discuss what could be the right challenge for specific employees of a company, So for example, now we started the challenge for bike to work for private companies, and we discovered that they really appreciate this because at the end of the month they have an extra salary if they use the bike,
Great.
But we never thought about before. Involving them is very important.
So very good discussion. So we have 1 minute left. We must close session at 11:10. So I leave the last sentence to Rogerio. He has a question about the social technical systems. Where are the social aspects?
No, I rather prefer. Sorry, thank you, Xiong. I rather prefer to close the session. All right.
Okay,
this is a parallel conversation that you're having a chat there between Nelly, a co-author of Antonio, and the stuff going on. All right.
All right.
So this is Cloudar discussion. All right. Thank you, Xiong. All right.
Great.
Okay. So everyone, the next session. Apologies for the delay. All right. That's why we are on Zoom and not on Cloudar, so we can reconfigure ourselves when needed. My apologies, but next session starts in 5 minutes, 15 past whatever the hour. All right. And yes, I just remind everyone, 5 minutes presentations, please, and focus on the discussions. Okay. All right. Great. I see you in 5 minutes. Bye-bye.